Hey everyone, welcome back to Dr. Ahmadi's YouTube channel. In today's video, we're diving into an incredible software tool that's a game changer for simulating photovoltaic systems. It's called PVsyst. So what makes PVsyst so special? It's super accurate because it takes shading effects, panel degradation, and performance analysis into account. Whether you're analyzing environmental factors or economic viability, PVsyst has you covered. Today we dive into the software interface through a practical project. The project we'll be working on is a 6 kilowatt grid connected system. To begin, click on the project tab and select new grid connected project. This opens a workspace for us. We can now rename the project to whatever we want. We can name our project, and to keep it simple and organized, I'll name it project underline 1. Next, we move on to importing the meteorological data. You can easily select the relevant data by clicking on this option. Yeah, this step is crucial because different locations receive varying levels of solar radiation and ambient temperature also differs, directly affecting the performance of the panels. So now we only have to search for our desired city. You can simply type the city's name in the search bar and click on search. Once you see the city's name appear on the right hand side of the screen, select it. Next, we have to import the meteorological data from one of the predefined databases. And one of the best options for that is Metanorm. After selecting Metanorm, click on import to bring in the data. And now we wait for the data to appear on the screen. It might take a moment. Yeah. Here you can view detailed meteorological data such as solar radiation, wind speed, temperature, and their respective units. On the right hand side of the screen, yeah, right here. We are not gonna change the defaults here. Once you've reviewed information, click OK to save the data. Yes, OK, save, and yes, there we go. In the next step, the project interface opens, and the first thing we do is to save the project. Next, click on the orientation option, which brings up a window where we can configure the system type and panel tilt angle. From the drop-down menu in the field type section, we can see a range of options, including both fixed and tracking types. However, for simplicity, we will choose the fixed type for this project. For the tilt angle, based on Tehran's latitude of approximately 33 degrees, we see that setting the panels at a 30-degree angle causes significant losses. By checking the data, we can find the best tilt angle with the least loss, which for this project is 35 degrees. This observation applies to the whole year, but it's clear that in summer a smaller tilt angle works better. While in winter, when the sun is lower in the sky, a larger tilt angle is needed. So obviously, the angle of the panels is crucial as it directly affects the amount of energy loss. Choosing the optimal angle plays a key role in the system's overall performance. Before moving on to the next step, let's save the project again. In this stage, we need to select the system design approach, which can be done in two ways. One way is to design based on the required area, and the other one is to design based on the desired power capacity. Since our project is for a 6 kilowatt system, we'll select the power-based option. Here we see that the unit for the rated power is kilowatts, so we just write 6. In the next step, we need to choose the PV module. The software provides a list of various manufacturers through the PVsyst library. For this project, we'll use the JA solar module. Within this module, there are different products with varying power output. It is worth noting that higher wattage panels in this list are newer and have a higher starting point, meaning that they take slightly longer to activate compared to lower wattage panels. For example, the 600-watt panels offer several advantages. They incorporate newer technology and they provide higher power in a smaller area. To achieve a total output of 6 kilowatts, We will need 10 of these 600-watt panels. For this project, we choose these 600-watt panels with newer technology, of course. The next step is to select an inverter for the system. Here we also encounter a range of manufacturers, but again we are going for Huawei company. One of the most important parameters is the inverter capacity. The inverter size must be slightly larger than the total system capacity to account for efficiency margins. For instance, if we select a 5 kilowatt inverter, the system is 6 kilowatts, and we are choosing a 5 kilowatt inverter, we'll get an error indicating that it's undersized. For example, here I choose a 5 kilowatt inverter to show you how the error looks like. If we run the simulation, here it's right, it's undersized. But to perfectly match system's capacity, we'll choose an inverter with a 6 kilowatt capacity. Finally, we will configure the circuit design by determining whether the panels should be connected in series or parallel. For example, we can set them in two branches of 5 panels, forming our 10 in total. But in this case, we will configure them entirely in series, meaning that we have only one branch of 10 panels, one after another. After completing the setup, click OK and save the project to finalize this stage. We hit the OK button and save the project here. In the next section, we will model system losses step by step. These losses are not detailed here for the sake of simplicity, but feel free to leave a comment if you'd like more information. In the horizon section, the effect of distant shading is modeled, showing how, for instance, the shadow of a distant mountain would affect the panel by adding the specifications of that object on the right-hand side of the screen. For our small system in this project, this aspect is not significant though. So we put our focus on close range shading in the 3D environment. To do this, we have to go back and click on near shadings and go to construction and perspective. In this environment, in the create tab, select the option single PV table. In this section, we see all the specifications of the panel. Here we set the tilt angle to 35 degrees to align with the previous settings. In the orientation section, you can choose between landscape or portrait, and you can see the difference between these two. As you can see, we have two parallel sets of modules, each consisting of 5 modules in series. To begin, we construct only the first set of 5 modules in series and add the second set later. In order to add the second set, again, we go to the Create tab, choose the single PV table, and set the specifications, like the tilt angle, according to the first one. Then we hit OK, and now we have two sets of modules in the construction environment that overlap one another. Therefore, we need to increase the distance between these two, as you can see. The critical question is, on the one hand, we want to maximize the distance to reduce shading effects, but on the other hand, we need to minimize the distance due to space limitations, aiming to fit the maximum number of panels within the available area. To find the minimum distance, we use the mathematical formula that you see right here in the Excel file. As you can see, to find the minimum distance, we need the panel length and the installation angles. These values have already been entered, resulting in the number 2.13 meters. In the following sections, we'll show where these numbers came from, but here the minimum distance between these two panels is determined. That's the most important thing for now. Before we apply the 2.13 meters of distance to the panels, I want to show you how I have extracted these values. Let's close this section and go to the system section. Here we hit the open button, a new window pops up giving information about the panel we chose. In the Size and Technology tab, we can see the details of the panel, things like the dimensions, weight, and module area. As you can see, the width of the panel is 1134 millimeters, but the value I used for the calculations was slightly larger. I did this to ensure a more reliable performance. Now that we know the required spacing between the panels, we return to the construction environment to adjust the distance between the two systems. We will use the measurement tool at the top of the screen for this. The calculated distance from the formula is 2.12 meters, which we'll input into the field on the right hand side of the screen. Next, we run the simulation to analyze the setup. As you can see, shadows are falling on the system, which from 9 a.m. to 3 p.m. shouldn't happen at all. This means that we need to adjust the panel positions slightly again. What we do is to increase the spacing between the panels from 2.12 meters to 2.3. We'll increase it slightly and run the simulation again. Although the situation improves, shadows are still visible on the rear panel. By incrementally increasing the spacing, we can reduce the shadows even more, but we lose space on the other hand. Once more, we attempt to reduce the shading effect by enhancing the distance to 2.4 meters and rerun the simulation to see the results. For a distance of 2.4 meters, we observe little shading from 9 a.m. to 3 p.m., which suggests that this distance seems sufficient for these two systems. We could increase the distance further, but sometimes, especially on rooftops, there simply isn't enough space. One important point to keep in mind is that other objects might also cast shadows on the panels. To simulate this, go to the Create tab, select the Elementary Shading Object section, and create the object you need. For example, we'll create an object here and place it on the eastern side. You can simply drag and drop the object to any position you like. Now let's see how much this object increases the shading and negatively impacts the performance of the PV panels. To analyze this, we place the object in the desired position and run the simulation. As shown, the shading caused by this object primarily affects the rear panels during the early hours of the day, because it's positioned on the eastern side. It's also worth pointing out that this simulation is performed during the worst time of the year, when the sun is low in the sky. So, what we see here is the most shading this object can potentially cause. The main question is, how can we reduce this impact? A potential solution is to increase the distance between the panels and the object. Running the simulation again shows a noticeable reduction in the shading's effects on the panels. Here, both from the tree views and from the top view, it is clear that the shading effect has been greatly reduced. In other words, we have successfully positioned the panels in a way that the shading caused by the object has no impact on them. Subsequently, as we close this scene and select the table option, we can accurately see the extent of the shading effect, like in what azimuth angle how much shading we have. We save it again and we run the simulation to see what's going on. The statistical data and power generation values can be seen here. However, for more detailed report, click on the report option. We wait until the report is generated. On the fifth page, important results can be viewed, such as the performance ratio, energy yield, and how much energy is injected into the power grid. These values are given in kilowatt hour per month, with the performance ratio provided for each month. One notable point is that the performance ratio is higher in the colder months because the temperature is lower, enhancing the performance of the panels. This results in higher peak production in the colder months, although the total production is higher in the warmer months. In other words, during colder months, the lower temperature helps PV panels work more efficiently, leading to a higher performance ratio. In warmer months, although the performance ratio is lower, the total energy produced by the panels is higher due to stronger sunlight we have. On the next page, you can also see the losses, which show how the generated energy has been wasted. If we had modeled the loss-related sections more accurately in the previous parts, this page would have provided more detailed information. Sources such as shading or losses due to temperature can be observed here. In the next section, the statistical data is available, and you can also see the single line diagram here. By clicking on the table option, hourly data can be retrieved. For example, information like the average energy production for each month, which is demonstrated here, or the system losses, or even weather data like radiation. One of the key strengths of this software is its ability to perform economic and environmental evaluations. For example, it allows us to model the system's carbon balance, showing how much greenhouse gas emissions are prevented by using this system. Here, we aim to briefly introduce this section by evaluating the carbon balance of our system. To do this, we go to the Economic Evaluation section and then we choose the Carbon Balance tab. Then in the Detailed System LCE, we select the panel, support, and inverter models. These components were selected earlier, and we know that the manufacturer company is based in China, so we choose China for all the components. This information is important for the software as the life cycle assessment varies between countries. In the overview section, we set the system's lifespan, which is typically 25 years but can vary based on maintenance and other factors. Here we'll assume a 25-year lifespan under ideal conditions. And finally, we select the grid electricity source, which in this case is from Iran. With this setup, we can determine that approximately 124 tons of carbon dioxide emissions are avoided. Moreover, a graph shows how many years it takes for the system to offset the amount of carbon dioxide emitted during the manufacturing of the PV panels. Now we return to the main menu and run the simulation. By navigating to the report section, we can see that new pages have been added, displaying the carbon balance details, including the amount of carbon dioxide emitted based on the life cycle assessment. As mentioned earlier, a certain amount of carbon dioxide is emitted during the manufacturing of the PV panels, approximately 11 tons in this case. However, by producing green electricity, the system eventually offsets this carbon with a total savings of 124 tons over its entire lifespan. The graph illustrates the point at which the system exceeds the carbon dioxide emitted during manufacturing, which occurs after about 2 to 3 years. Beyond that, the system continues to generate green solar energy without releasing harmful greenhouse gases. And that wraps up our quick yet insightful dive into the PVsyst software, showcasing its powerful tools and features. Whether it's optimizing panel placement, assessing shading impacts, or performing environmental evaluations, PVsyst truly empowers solar energy projects. Thanks for watching, and if you found this helpful, don't forget to share this video with your friends.